Good day, I'm Norman Wahlberger and welcome to 2016. In today's video we're going to be looking at some fundamental counting problems that are very essential in modern combinatorics. And they're really associated with these four types of data structures that we've been talking about in the last few videos. Lists, ordered sets, multisets, and sets. And each one of these can be thought of in terms of two numbers n and k. So we talk about k lists from n, or k ordered sets from n, k multisets from n, and just k sets from n. And in each of those cases we can ask how many of each of them are there. It's a question of counting. So these are almost surely the four most basic counting problems in mathematics, or at least certainly in combinatorics. So today we're going to address those, and there's some rather familiar answers, but perhaps some unfamiliar ones too. So our first counting problem is to understand how many lists there are, which are k lists from n. So while list nk is for us a type, so we refer to a data structure having this particular type, we are still going to use this somewhat familiar notation for the size, or in other words, the number of objects which actually have this type. So at this point, this is not a set, but we are going to use the same kind of notation. And here's the basic formula that we want to establish, that the number of lists which are from n and have size k is n to the k. So I remind you that n here is a natural number, 1, 2, 3, 4, 5, and so on. And k can be also a natural number, or possibly 0 as well. This is a very easy counting problem because a list is such a concrete, easy to understand kind of object. So here's a typical list. Here's a list with k objects, L1, L2 up to Lk, and each of these is a natural number somewhere between 1 and n, because we're assuming we have a list from n. So it means that all the entries are within the range 1 to n. And they're ordered. So there's a first one, there's a second one, all the way up to a kth one. So how many of them are there? Well, it's a very simple situation, because there are n possibilities for the L1. L1 could be 1, 2, all the way up to n. There are exactly n possibilities. And similarly, there are exactly n possibilities for L2. And similarly, there are exactly n possibilities for all of the L's, including Lk. Because repetitions are allowed, these various choices are completely independent. So there's n possibilities here, all the way up to n possibilities here. And so the total number of possibilities is n times n, so on, all the way up to times n, where there are in fact k of these n's multiplying together, because there are k entries in our list. And that's why we have n to the k as the number of such lists. Okay, good. So our next counting problem is to count ordered sets. We're talking about k ordered sets from n. And the formula is that the number of O set nk's is equal to n to the k following. We're using here Knuth's notation that we talked about in Math Foundations 55 when we were talking about the binomial theorem and binomial coefficients. So Donald Knuth introduced the very pleasant, kind of efficient way of talking about what happens when you multiply an n by n plus 1 by n plus 2 and so on, and altogether k such increasing things multiplied together. That was nk rising. And if we start with n and we multiply then n minus 1 and n minus 2, so all the successively lower ones, k terms altogether, then we have n to the k following. So this is n times n minus 1 times n minus 2 all the way to n minus k plus 1. Now that ensures that there are altogether k terms being multiplied there. So it's this one here that's involved in the formula. So in fact it's very similar to the number of lists, except that instead of being n to the k, it's n to the k falling. And the reason it's not very hard, I remind you that an ordered set looks something like this. So here's a KO set. It has k elements. It has these braces here that tells us that repetitions are not allowed. But otherwise, the entries can, just as before, be any natural numbers from 1 to n. But there's an order. So this is the first one, the second one, and so on. So it's just like a list, except that repetitions are not allowed. So if we want to count how many there are, it's not too hard, because there are n possibilities for this first one. And then, as opposed to a list, there are no longer n possibilities for the second one, because repetitions are not allowed. So whichever one that we've chosen for L1, L2 has to be different from that one, leaving only n minus 1 possible choices for L2. And then L3, there will only be n minus 2 choices for it, because we can't repeat the L1 or the L2 value. So at each stage, the number of options decreases by 1, so we're picking up exactly falling power in the sense of Knuth. And there are going to be altogether k such terms in this product, because there are k choices to be made. So n times n minus 1 times n minus 2 all the way down to n minus k plus 1. That's exactly this thing here, n to the k falling. It's the number of ordered sets from n with k elements. Or if you like, the number of KO sets from n. Also a very fundamental counting formula. For our next one, we're going to skip ahead to the set case. So we're going to count the number of sets from n with exactly k elements, or the number of sets that you can make using the numbers 1 through n and choosing exactly k elements. The answer is the familiar binomial coefficient, n choose k, written usually with these brackets, and we've talked about those kinds of numbers and their role in that Math Foundations 55 video and the ones around it. I remind you that the binomial coefficient n choose k can be written in terms of the factorial as n factorial over k factorial times n minus k factorial. And I remind you that k factorial is just k times k minus 1 times k minus 2 all the way down to times 1. In fact, that's also a falling power. It's k to the k falling, because we're starting with k, and then there are exactly k terms in this product. So we could rewrite this binomial coefficient as a quotient of two falling powers. The n factorial over n minus k factorial. That's what you get when you have n times n minus 1 all the way down to the one above that, which is n minus k plus 1. Well, that's exactly what we called n to the k falling in our previous slide. So this divided by this is n to the k falling, and then there's a k factorial, or a k to the k falling, in the denominator. Okay, so how can we see this familiar formula? Well, one way is to connect it to what we've just done with O sets, because there's an intimate connection between sets and ordered sets. If we have a set like this, and it's a k set from n, so it has k elements, and each of these elements is a number between 1 and n. But the elements here are unordered. If we want to make an ordered set from this, we can do that in exactly k factorial ways, because we can order these k elements in exactly k factorial ways. We can choose a first one in k ways, and then a second one in k minus 1 way, and then a third one in k minus 2 ways, and so on. So a k set S like this can be ordered in k factorial ways. That means that there's a relationship between the number of O sets of size k from n and the number of sets of size k from n. If we take a set of size k from n and multiply it by k factorial, we're getting all the k factorial possible ordered sets that can be created from that original unordered set. So it follows that the number of ordered sets is k factorial times the number of sets. And we know what this is because we've just found that in our previous slide. That was n to the k falling. And so it follows that set nk, the number of sets of size k from n, is going to be this n to the k falling divided by the k factorial. It's exactly what we have here. The n to the k falling, that's the number of O sets of size k from n. And this k to the k falling, otherwise known as k factorial, is just coming from here. So again, a very familiar kind of thing, and if you've played around with the binomial theorem or you remember the discussion around Math Foundations 54, 55, and so on, this will be very familiar to you. So these three are relatively simple. The fourth one is considerably trickier and less well known. The problem of how to count multisets. Okay, so now we turn our attention to this problem. The trickiest of the problem is to count the number of m sets from n of size k. So k m set from n has the form like this. You have square brackets denoting the fact that repetitions are allowed, but there are no commas now telling us that we can rearrange things and things don't matter. So it's an unordered object. So here's m, there's k objects because we're assuming we have a km set, and all of these are numbers from 1 to n, and very possibly there could be repetitions. How many of these are there? Well, to count that, let's remind ourselves that we had an alternate way of expressing or writing down an m set. Maybe we call that the multiplicity form for m at some point. And here is the alternate way of writing such an m set. We use the fact that we can add m sets and that we can multiply m sets by numbers to represent multiplicities. So we can write it as m1 times the m set 1 plus m2 times the m set 2 all the way up to mn times the m set n. What we're doing here is we're simply counting in this multiset the number of ones, and that's m1. So m1 is just the multiplicity of 1. m2 is the multiplicity of 2 in here. We count how many 2's there are. We count how many 3's there are, and so on, up till the number n. We count how many n's there are, and that's m sub n. So another way of asking the question is, how many such expressions are there where, what do we know about the m's? Well, the m's are multiplicities. So they have to be natural numbers or possibly 0. It's very important to remember that 0 is allowed as a multiplicity. It's not necessarily the case that all of these are going to appear, and generally they don't. Okay? So the multiplicities mi are all positive. When I say positive, I mean greater than or equal to 0. And in fact, they're all less than or equal to k because we're assuming that there's k objects in this m set altogether. So clearly any one of them can only occur at most k times. And the other thing that we know about the m's is that if we add them all up, well, that's the total number of objects in the m set, which is the size of the m set, which is k. These conditions then are another way of thinking about what the problem is. We're trying to find out how many solutions to finding m1, m2 up to mn where they sum to k and they're all positive. In fact, this condition that they're all less than or equal to k is really not entirely needed. It's true, but it's not really needed. Once we know that they're all positive, then this condition will guarantee that none of them is bigger than k. So we don't actually need this condition. We could just think about having a condition that we have looking for positive m's that satisfy that their sum is equal to k. We want to know how many such solutions are there. Now there's a rather clever argument here. Now if you've taken a discrete mathematics course or a combinatorics course, you will have seen this argument because it's a very fundamental one. But many of you will not have seen that, so it's probably better to start with a special case. If we're looking for some pattern or some formula and it's maybe a little bit tricky, we don't know what to do, looking at special cases where we can work things out, see what the pattern is a very good way to start. So let's have a look at something like MSET 5,3. It actually fits in with what we've been using as example quite a lot when n is 5. So what do MSETs 5,3 look like? Well, we're talking about 3 MSETs from 5. So all the elements have to be numbers 1, 2, 3, 4, 5. Those are the possibilities for the entries. And there have to be 3 entries altogether. And order doesn't matter, and repetitions are allowed. So here is a 3 MSET from 5, 1, 1, 1. Here's another one, 1, 1, 2. Here's another one, 1, 1, 3. 1, 1, 4, 1, 1, 5. 1, 2, 2. 1, 2, 3. And so on. There's quite a few of them. There would be another one, 2, 4, 4. And we could list them all. We want to know, for example, how many are there just of this kind. So let's have a look at the question in this particular case. So in this situation, we're looking at an MSET where the objects are one of these numbers 1 through 5. So we can write this MSET as some number of 1s plus some number of 2s plus some number of 3s plus some number of 4s plus some number of 5s. And these multiplicities have to add up to 3 because altogether there have to be exactly 3 elements in our MSET. And we've said that we can think about the inequality as just that they're all positive or greater than or equal to 0. Okay, so how are we going to count how many solutions there are to essentially this pair of equations? Okay, so now there's a little bit of a trick here, which is to employ some kind of physical representation of these various MSETs. And what we're going to do is we're going to take these 5 multiplicities and arrange them in order separated by lines. So these lines that we're drawing here are sort of like dividers that separates the M1s from the M2s, from the M3s, from the M4s, from the M5s. And if we're looking at a particular MSET like this one, it has 1, 2, and 2 4s. We're going to represent that in this diagram by making some circles. So we're going to make 3 circles, 1 for each one of these entries. So there's a 2, so we're going to put a circle in the little box labeled M2. And there are 2 4s, so we're going to put 2 circles in the sort of box labeled M4. So notice that these 4 dividers actually give us 5 regions. There's the M1 region before the first divider, then there's M2, and then there's M3, and then there's M4, and then there's M5 after the last divider. So to get the 5 regions, we need 4 dividers. That's going to be an important point. So this is a way of associating to a particular MSET of the kind that we're interested in, a particular configuration of circles and lines. In fact, this configuration has exactly 3 circles representing the 3 entries and 4 lines representing the divisions or the separators between these 5 different multiplicities that we're interested in. So I want to do some more examples like that to let you see what's going on here. Okay, so let's look at this MSET, 1, 1, 5. What pattern of circles and lines corresponds to it? Well, there's our 4 lines which separate the regions into these 5 boxes, each one corresponding to a multiplicity of 1, 2, 3, 4, 5. So over here we have 2 1s. So we're going to put 2 circles in the M1 box, the first box. There are no 2s, so that's going to be empty. There are no 3s, there are no 4s, and there's a single 5 that goes there. So this pattern of circles and dividers represents this. If we didn't have this and we just looked here, we'd see, there's 2 1s, no 2s, no 3s, no 4s, and 1 5. Okay, how about 2 3 4? There's 0 1s, there's a 2, there's a 3, there's a 4. 1 5 5. There's a single 1, there's no 2s, no 3s, no 4s, and 2 5s. Let's go the other way around. So here we have a situation, we have 4 dividers and 3 circles. What M set does that correspond to? Well, we read off how many 1s that are there. There's 0 1s, there's 0 2s, there's 2 3s. Okay, so we have to put 2 3s. And no 4s and 1 5. So it corresponds to the M set 3 3 5. How about this one? Line, 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 circle, 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 line. Well, there's 0 1s, 0 2s, 0 3s, 3 4s. Okay, so there's 3 4s. And of course, no 5s. So it corresponds to the M set 4 4 4. And what about this one here? Circle, circle, line, line, circle, line, line. That corresponds to, well, there's 2 1s, there's no 2s, there's a 3, no 4s and no 5s. So I hope you can see that this way, every M set from 5 with exactly 3 elements corresponds to a picture like this that has exactly 4 lines and exactly 3 circles, and the actual positions of the lines and circles are arbitrary. I mean, the lines are all in order, but the relative positions of the circles could be anywhere, before the lines, after the lines, or interspersed around. So if we want to count M sets, another way of doing it is to count the number of these geometrical patterns of circles and lines. And that's actually not too hard to do. So any multiset M from 5, size 3, corresponds to a pattern of 3 circles and 5 minus 1 dividers, or lines. And these can be in any order. There's no restriction on the relative positions of these 3 circles and 4 dividers, as long as they're all just in an order. Well, we can count that, because that's really the situation where we have 7 objects altogether, because there's 4 lines and 3 circles, and we have to choose 3 of those 7 to be circles. So consider this one here, for example, right? There's altogether 1, 2, 3, 4, 5, 6, 7 objects. There are always 7 objects. And this one is specified by the circles being the 1, 2, 3, the 4th, the 5th, and the 6th. Here, the 3 circles are the 1st, the 2nd, and the 5th of these 1, 2, 3, 4, 5, 6, 7 objects. Altogether, there are 7 choose 3 such patterns of circles and lines. And 7 choose 3 is a binomial coefficient. One way of saying it is that it's 7 to the 3 falling over 3 factorial. That's a very efficient way of calculating it. So it's 7 times 6 times 5. There's the 7 to the 3 falling. Divided by the 3 factorial, 3 times 2 times 1. Then a bit of cancellation, the 3 times 2 and the 6 cancel, and we just get 35. So there are, in fact, 35 M sets from 5 with exactly 3 elements. And if you're not sure, you could write them all down and count them and make sure that that actually is the case. Okay, so if we absorb this specific argument, the general case is really not too much different. Here is the formula for the number of km sets from n. It's also a binomial coefficient, but it's formed from the n and the k in somewhat more complicated way. It's n plus k minus 1, choose k. And the reason is because what we're counting is the number of solutions to the equation m1 plus m2 plus all the way up to mn equals k. We're assuming that there are n possible numbers that can be ingredients. So the multiplicities go from the multiplicity of 1 all the way up to a multiplicity of n. And we've said that there are going to be k objects in this M set altogether, so the total number of multiplicities have to add up to k. And they all have to be positive, greater than or equal to 0. So the number of solutions to this, well, it's the same as the number of ways of placing k circles and n minus 1 dividers. These n multiplicities can be represented by these sort of m positions that are obtained with these n minus 1 dividers. And then we have to choose k circles interspersed amongst those n minus 1 dividers. So altogether there are then n minus 1 plus k, or n plus k minus 1, objects in our diagram. There are n minus 1 dividers and k circles. And from those we have to choose k circles. So altogether we have n plus k minus 1, choose k. That's the number of M sets from n of size k. That's a very important counting problem, and it sort of closes the circle on these sort of elementary data structures and counting how many objects there are in each one of them. So very good. We now want to go a little bit further though, because now we've got these 4 types of data structures, very nice. We'd like to be able to make a little bit more sophisticated objects. We want to be able to combine these things. We want to consider lists whose elements are not necessarily just natural numbers, but maybe whose elements are themselves sets, or perhaps ordered sets, or perhaps multi-sets. You can see now there's going to be a lot more combinations and possibilities, and things are going to become more complicated. So we want to enlarge our view by having more data structures, still starting from these 4 basic types and combining them in more elaborate ways. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.